everyone, myself Srivalli, working as an assistant professor in the Department of Cybersecurity and Data Science in MLR Institute of Technology. Today, the overview of presentation includes walk, trail, path, cycle and circuit, subgraph, which is nothing but the types of subgraph we have spanning and induced subgraph, and we also have vertex disjoint and edge disjoint subgraphs in the subgraph concept, and also we have the last concept that is called isomorphism. So let us see here what is walk, trail, path, cycles and circuits. So first let us go for walk. So basically here walk is nothing but you are just traversing from one node to another node. Just visiting the nodes, so one by one, that is called just a walk. A walk is sequence of vertices and edges of a graph. Means here sequence of vertices means here A to B, B to D, D to A. This is one walk. So means if we traverse the graph, if your walk is nothing but sequence of vertices and edges of a graph, that is nothing but if you traverse a graph, then we can say that it is a walk. So here in this walk, vertices can be repeated, edges also can be repeated, and this walk can be opened or closed also. So a walk can be repeated anything. So here edges or vertices. So in the view of the graph walk, so where it is visiting from vertex, one vertex to another vertex, so it can be repeated anything, either edges can be repeated or vertices also can be repeated. So here the walk is A, B, so here walk is A, B, D, E, C. So not only this one, you can also consider A, C, E, D, B. So this is open walk. If I attach from B to A, this is called closed one. So this is walk here, and we also have trail, a walk in which no edges repeated. So whenever you are walking here, edges should not repeat. Then we can say that we will get a trail. So trail, there here vertex can be repeated, but edges should not be repeated. So let us suppose here A to B, B to D, D to E, C to E to C, C to A. So now A, B, C, E, D is also trail. A, B, C, E, D is a trail. Also A, B, C, E, D, A, B, C, E, D, and also B. This is a closed trail here. So here we can say that here the vertices should repeat and edges should not repeat. That's why if you observe here in the closed trail, so B is repeating twice. So A, B, C, E, D, B. So A, B, C, E, D is an open trail. Next we also have circuit. So traversing a graph such that no edge should be repeated, but vertex can be repeated and it is closed also. That is, it is a closed trail. So here traversing a graph, no edge should be repeated and vertex can be repeated, but it should be always a closed one. So see, let us suppose here. So we have here 1, 3, 6, 8. So here 8, 4, 2, 1. So in the same way here 1, 2, 4, 6, 8, 3, 4. This is also closed one here. So in the same way here, so 1, 2, 4, 8, 6, 3. This is also closed one. So like this here, no edges should be repeated, but vertices can be repeated. That is called circuit. So next we also have here path. So it is a trail in which neither vertices nor edges should be repeated. So just observe the difference between the previous one and here. There edges should not repeat, vertices can be repeated, but here no vertices or edges should be repeated. So if you are traversing a graph, so that we do not repeat a vertex and nor we do not repeat an edge, and here vertex and edge will not be repeated. So let us suppose 1, 2, 3, 8, 6 like this. So means here see 1, 3, 2, 1. So here if you observe here 6831, 6831 and 6832 also. So 6832 and even we have 2386. So also we have 4, 5, 4, 5, 7, 8, 6. So like this, no vertices should be repeated, edges also should be repeated here. So in the same way we have cycle also. So here what is meant by cycle is traversing a graph such that we do not repeat a vertex, nor we do not repeat an edge, but the starting and ending vertex is always same. So here that is we can repeat the starting and ending vertex only, then we will get a cycle. So as in we have seen cyclic graph is nothing but starting and ending vertices must be same. So except that the other edges and vertices should not be repeated. So here vertex and edge will not be repeated. So we can say this cycle is a closed path. So 1, 2, 4, 3, 1. Or else 2, 3, 5, 4, 2. Means always the starting and ending vertices are same here. Even we have here 1, 3, 4, 2, 1. So 1, 3, 4, 2, 1. So this is called one cycle. And also we have 3, 5, 4, 2, 3. This is also one cycle, closed one. So this is called a cycle. Now let us see the new concept here, subgraph. So what is meant by subgraph is, let us suppose we are having two graphs. So what are the two graphs here I am representing? First graph as original graph as Z and the other graph as Z1. So just here ignore this G1, F1, H1. So these are the names I have given, but here I am representing with the first graph as original graph as Z and another graph as Z1. Now we can say G1, this G1 is a subgraph of this particular G if it satisfies two conditions. So here carefully here look, we have the four figures. Out of the four figures, first two here I am taking, and the first one as original graph, and the second one here I am taking another graph which is representing with G1. Now this G1 is called a subgraph of G if it satisfies two conditions, and those two conditions are all the vertices and all the edges of G1 are in G. So all the vertices. So here if you observe all the vertices of G1, what are the vertices of G1? V1, V2, V3, V4, V5. So it should be in G. Yes, V1, V2, V3, V4, V5. Each edge of G1 has the same end vertices in G as in G. Each edge of G1. So each edge of G1 means what? This one for example, each edge of G1 has the same end vertices in G as in G1. So V1 and V2 are having the same vertices and they have edge. So V1 and V2 are having. And V1, V3, yes, V1, V3 is having edge. V2, V4, yes, V2, V4. V3, V5, V3, V5. And V4, V5 here, also V4, V5. Means whatever the vertices along with the edges we have, the same end vertices edge should be there in G1 also, G also, as in G1. So then, if these two conditions are satisfying, then I can say that this is called a subgraph. So this first one is called a subgraph. Why? Because all the vertices are there in G1, so original graph, and all the edges of end vertices are same as in G. So I can say this particular graph is called what we can say this is called subgraph. So let us consider other graph. Here we have H1. Let us consider this H1 is a subgraph of G1 or not. So let us suppose V1. Yes, V1 is there. V2, V3, V4, V5. Yes, we have. First condition is satisfying here. Each edge of G1. So let us suppose consider this is G1, V2, V3. So each edge of G1 has the same V2, V3. Yes, V2, V3 same edges. And V3, V5, yes. So and V2, V4, yes, same edges we have. V4, V5, yes, same edges we have. But here if you observe, here we don't have any edge. Even if you have or not, it doesn't matter here. If you have one edge here, so now the same end vertices must be there in G1. So I don't have any vertex here. I will not care about this one. So this is also called subgraph. In the same way, if you go with the next one, J1, let us see whether this J1 is called a subgraph of G1 or not. So the vertices V2, V3, V4, V5. Yes, V2, V3, V4, V5 we have. And V2, V4 connectivity is there. V3 to V5 connectivity is there. V4 to V5 is also connectivity there. And now here V2 to V3. Yes, I don't have any connectivity here. So vertices means whatever the vertices I have in this small graph, that should be there here. and the edges, the same edges, same end edges must be there in the main graph. So all these conditions are satisfying. That's why even this is also called a subgraph. Then what is meant by spanning subgraph? We have different types of, we have seen only what is meant by subgraph. Now we have also have different types of subgraphs, that is called, out of that first one is spanning subgraph. So given a graph G is equal to V comma E, and if there is a subgraph G1 V1 E1, it means here I am representing the main graph with G, where I have the vertices V comma E, and here I am representing G1, where I am representing this vertices edges as V1 E1 of G, such that V1 is equal to V. So here this is V1 and this is V. So whichever the vertices I have in the subgraph, those vertices must be equal to the main graph. So here if you observe, I have, let us, I am denoting with A, B, C vertices, and here if you take this is G1, here also A, B, C. So now if you observe, the vertices V1 is equal to V here. So like this, if you see, all are having the vertices equal to main graph. So that's why I can say that this is called a spanning graph. This is called a spanning graph. So next we also have induced subgraph. So what is meant by induced subgraph is here. Suppose we have a graph G is equal to V comma E. There is a subgraph G1 is equal to V1 E1 of G, such that every edge A comma B of G, where A comma B belongs to V, is an edge of G1. Here G1 is known as subgraph of G induced by V1, and it is denoted by V1. So what is the meaning here is, just observe here. So this is a graph here. So how I can say this graph is called subgraph is, so whatever the vertices I have, for example, here I am denoting the vertices with A, B, C, D, E. Now I have A, yes it is there, B it is there, and sorry it is C, and this is D, and this is B. So whichever the vertices I have in the subgraph, those are vertices which are there in main graph. So not only that, so I have edge A to C, yes here I have edge A to C. C2D edge is there, C2D edge is there. B2D edge is there, here also B2D. You forget about whether vertices E is there or not, B to A is edge is not there or not, you forget about. So whichever the vertices we have, and those vertices are there in the main graph or not, whichever the same edge points we have, those are there in the main graph or not, you have to check it. So then it is called subgraph. Then is it a spanning subgraph? So I have A, B, C, D, E. Now these vertices V1 is equal to V, then it is called a spanning subgraph. Then what is meant by induced subgraph? So here we have a definition induced. Suppose we have a graph G V comma E. So this one I am denoting with G V comma E. There is a subgraph G1 V1 E1. So let us suppose here I am representing G1 is equal to V1 E1. So V1 E1 of G, such that every edge A comma B of G, so means whatever the edge we have, let us suppose here edges points are B, C, D. So every edge AB of G, every edge A of G belongs to V is an edge of G1. So which is nothing but here. So let us suppose here B to C. There is a edge here. Yes, it is a edge. And C to D. Yes, it is a edge here we have. And B to D as I have. Let us suppose if I have E and E to D is there, but E to B is not there. So then I can say this is not an induced subgraph. Means if you have vertex and if there is a connectivity from one vertex to another vertex, but if that is not there in the subgraph, then I can say that is not an induced subgraph. Definitely it should point towards E to B also, as we have connectivity in E to B in main graph. So this is called subgraph here. So next we have vertex disjoint and edge disjoint subgraphs. So what are vertex disjoint and edge disjoint? So in the name itself we have disjoint is nothing but whenever you are combining, and if you are going to take the common values, so definitely you should get 5, means common values you should not get here. So in the same way in terms of vertex and edge, So whenever you are combining the vertices, you should not get the common vertex or edge. Then only we can say that it is called disjoint, vertex disjoint subgraph or edge disjoint subgraph. So let us see the definition here. If G is a graph and G1, G2 are two subgraphs. So let us suppose this is the original graph now. So I am considering with capital G. And this is G1 and this is G2 subgraphs here. So here they have mentioned very clearly that G1, G2 are subgraphs. Then G1, G2 are said to be vertex disjoint. How I can say that G1 and G2 are vertex disjoint if they don't have common vertex? So now I have, so here what I have done is this original graph I have just I have broken down into two different graphs. In view of this, no vertex is common here. So what are the common vertices here? If you observe here, this is vertex disjoint, no? So this is Z1 and this is Z2. So A, B, E, C, D, F. So now if you observe here, so altogether how many vertices we have? 6 vertices. And the 6 vertices are distributed to remaining 2. So A, B, E, C, D, F. So which is nothing but here I don't have any common vertex in between these two. Then I can say that this is called vertex disjoint. No vertex is common here while the graph is disconnected. So in the same way, it is applicable for edge disjoint graph also. So let us suppose G1 and G2 are I have. So now it is said to be edge disjoint graph if they don't have any common edge. So don't have common edge means what? So A, B, C, D, E, F. So this is A, B, C, D, E, F. But the leftover edges are what? B, C, E, F. So here vertices are common, repeated, but edges did not repeated. So then I can say that as no edge is common here, I can say this is called edge disjoint subgraph. So next we have isomorphism. So what is isomorphism here? So isomorphic graphs, two graphs G and G power or G1 or G dash are said to be isomorphic if there is a function f v2g dash such that f must be a bijection. Bijection is nothing but it should satisfy 1 1 and on 2. And for each pair of vertices u and v of g, so for u comma v belongs to e of g and f of u f of v belongs to e of g, then that is the function preserves adjacency. So if G is isomorphic to G dash, then we can say mod V of G is equal to mod V of G1 and mod E of G is equal to mod E of G dash. So two graphs of same order, same size need not be isomorphic. So it is not the case that here if you have two graphs where they have same order and same size, so they are not need not be isomorphic here. So this is just a formal definition we have, and we have also have the definition where you can understand very clearly here. So two graphs are isomorphic if they are structurally identical, and which means that they are correspond in all structural details. Formal vertex to vertex and edge to edge correspondence is called isomorphism. Means if you consider two graphs here and if both the graphs are having same number of edges, same number of vertices, same number of degree, then we can say that both the graphs are called isomorphic to each other. So two graphs are said to be isomorphic if they have same number of vertices, same number of edges, they have an equal number of vertices with a given degree. So let us consider one example so that you can understand very clearly that how you can find out, verify that the two graphs, given graphs are isomorphic to each other. So here I have considered graph A and here I have considered graph B. And in this, the vertices are here A, B, C, D, E. So A, B, C, D, E. And here I have considered P, Q, R, S, T. So, and even I have edges also. So now I have to check whether this graph A is isomorphic to graph B or not. So in view of this, first what you have to do is, first you need to check as per our conditions, you have to check how many number of vertices are there in graph A and graph B, how many number of edges are there in graph A and graph B, and whether they have same number of degree vertices we have in both, that you have to check. So let us suppose vertices A. So in vertices A, so there is nothing but graph A. So you have how many? So A, B, C, D, E, Q, P, R, S, T. Now here A is pointing towards Q B is pointing towards P. Why? Because if you find out degree, what is the degree of A here? 1, 2. And if you find out P here, degree of P is what here? So degree of P is 1, 2, 3. Means A is not equal to P. So then you go for Q here. Q is having 2. Then I can say A is equal to Q here. So it is not the thing that here if you have first vertex in the second graph, you will have the first vertex only the same thing. So if you take B, B is having 3 and P is having 3. So I can point out B is equal to P vertex in the graph B. In the same way, C if you take 2 and R if you take again 3, yes you have 2. So here R is having here PQR, R is having 3S. So here you can take yes, D you can take. So here C is having 3 here. So D is having yes and E is having here T. So these are equal to B to P, C to R, D to S and E to T. Now the vertices here, the degree of the vertices, based on the degree of the vertices, you are equating the vertices of both the graphs. Now edges also you have to consider. Edges of A, edges of B. E1, E2, E3, E4, E5, E6. And also here E-1, E-4, E-3, E-2. Means this edge E1 is mapping with equal to E-1. E2 is mapping with E-4. E3 is mapping with E-3. E4 is mapping with E-2. E5 is mapping with E-5, E6. Means based upon the number of the edges, you are equating the which vertices are equal to which vertices in both the graphs and also the edges. So here if you observe, we have another example, the same thing here, whether both the graphs are isomorphic or not. So first two conditions 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Same number of vertices we have and also edges 1, 2, 3, 4, 5. And this is 1, 2, 3, 4. So here 1, 2 and this is 3, 4, 5. So we have all the 5 edges. Now if you see here, so which one is mapping with which one? So E1 is having the degree is 2. So E2 is having degree 2. And E3 is also 2, E4 is also 2. And E5 is also 2. In the same way here, C1, so C1 is mapping with 2. And C2 is mapping with 2. So C3 is mapping with 2. C4 is 2. C5 is 2. So based upon the number of the degree of the vertices, so you can say that this graph G is and G1 are both isomorphic in nature. So what we have discussed today in this session is, so what are walk, trail, path, circuit, cycle, and also we have discussed what is meant by subgraph, what are the types of subgraph like spanning subgraph, induced subgraph, and what is meant by isomorphic and how we can say that the given two graphs are isomorphic in nature. So by this, today we'll end the session. Thank you.